Hey everybody, welcome to 5.2. This is the follow to integer addition and subtraction. This is multiplication and division. So it is much the same kind of stuff we've been talking about. It's just the other two operations, right? So once again, we are squarely down here in the integers, in the natural numbers, which is, the integers, which is the natural numbers 0. Together, those make whole numbers and negative natural numbers. We're going to start by talking about multiplication models. One of the ways to start talking about this with kids is really to go back to the idea of repeated addition, right? If I have 3 times -2, that means I have 3 -2s. So I could add -2 plus -2 plus -2. That it makes sense that if I owe you $2 and then I owe you 2 more and then I owe you 2 more, I'm going to owe you $6. That's -6. So it then makes sense that 3 times -2 is -6. You can also find from there, using commutative property, that -2 times 3 is -6. These are all equivalent. And then we can use that to find patterns, right? So if 3 times -2 is -6, then 2 times -2 would be -2 plus -2. That would give me, this should be -4. 1 times -2 is -2. 0 times anything is 0. And then if we keep counting our way backwards, we back ourselves into this idea that a negative times a negative is positive. So if I have -1 times -2, it's really hard to do a repeated addition version of that, isn't it? But I've used my pattern. I can see I'm counting up by 2s, so I can tell from my pattern that -1 times -2 is 2. -2 times -2 is 4. -3 times -2 is 6. And this is sort of the beginning of this idea. One of the other models is a return to the chip and the charge fields. So you make groups in this case. So you make groups of whatever kind of chip it is you're multiplying. So 3 times -2, if our red chips are our negatives and our black chips are positives, 3 times -2 is 3 groups of -2. Well, if I make 3 groups of -2 chips, I have -6 worth of chips. Same thing with the charges. Charge field. I have 3 groups of -2 negative charges, okay? So how do we do that with what we're doing down here? Let's try these examples at the bottom. So I have 4 times -1. Well, that's really just 4 sets of -1 chips, right? 1, 2, 3, 4. That gets me a total of -4. -2 times 2, like this isn't a useful way to think about that. I'm not going to think of -2 groups of 2. So instead, I'm going to think about it in the other direction, because multiplication is commutative, right? I do whatever I want. I have 2 groups of -2. So 2 groups with -2 in each, also going to get me -4. Okay, and then this is the same question again. All right, so you see how that goes? Let's see what happens if we do it a little differently. So if we need -3 times -2, this is where the chips get kind of weird, right? So I can think of that as removing, right? As removing 6 negative chips, or yes, and see what's left. So I'm going to start with 3 groups of -2. I'm going to start with I'm going to start with as many zeros as it takes me to get 6 negative chips, because I know 3 groups of -2 would be -6. Okay, so I'm going to say that again. I'm going to start with as many zeros as I can need to get -6. So there's 1, 2, 3, 4, 5, 6 sets of 0 here. Remember, 0 pairs. I'm going to take away, I'm going to use this negative as a takeaway. I'm going to take away 6 negative chips, 3 groups of 2 sets of negative chips. If I take those away, I'm left with positive 6. This is when sort of the chip model starts to be kind of convoluted. It works really well for some kids and not for others. So you can, so it's worth showing to kids and doing. And then for the kids that love it, it's like, oh, okay, I get it. And for the kids that don't, that's fine. So the first one here, if we look at these examples, I want -4 times -1. So I'm still going to say, this is going to be, I'm going to take away 4 sets of -1. So if that's the case, I need to start with 4 zeros to start. All right. And then I'm going to take out my 4 sets of -1. That leaves me with 4. Okay? We're going to do this one next. So this one says take away 3 sets of -4, right? So if I'm going to take away 3 sets of -4, I need 3 sets of -4 to start. So that's 1 set, through sets, 3 sets. I'm going to make them zeros. And now I can take away my 3 sets. There's 1 set, 2 sets, 3 sets of -4, leaves me with a positive 12. Okay? It's different. You got to think through it a little bit, but it is a useful thing to show kids. Okay? Charge fields work the same way. It's the same as we talked about in the last lesson. It is the same process as chips. This is just one level of abstraction up, right? So instead of moving around chips, they're going to draw plus and minus signs, and that's fine. Excuse me. So that you can, this works the same way. We put in our 6 zeros. We take away our 3 groups of -2. The other model in multiplication is the number line. This gets also a little more complicated. So you have to stick with the story here. You ready? So you're imagining a hiker moving on a number line. Okay? When he goes to the left, he's moving in the negative direction. When he goes to the right, he's moving in the positive direction. This is where it gets weird. Time in the future is a positive value. Okay? Time in the past is negative. So he's moving for a period of time. We have 2 dimensions here almost, okay? This is thinking about a way to capture the idea of moving forward or backwards in groups in a positive or negative direction, right? Okay, so I want to be at 0. This is where I'm starting my trip. I'm going to move east, which was to the right, at 3 miles an hour. Where will I be in 4 hours? Well, in 4 hours, if I'm going 3 miles per hour, there's 3, 6, 9, 12. I'll be 12 miles east of 0, which is the same as positive 12. Okay? If I'm now at 0, and I'm going to move east at 3 miles an hour, where was I 4 hours ago? So 4 hours before now. That's time in the past. That's a negative value. I'm going to move to the left to get time in the past. Okay? So 4 hours before now, I was 12 miles west, which is the same on the number line as -12. We don't think about negative distances, but this is another way to think about this, okay? If kids are using number lines a lot, this actually, for us, feels a little weird to think about it this way, but for kids that are super comfortable with number lines and use them to do lots of different things, this actually isn't so bad. They go like, oh, okay, time forward, time backward. They're much more accepting of this as not a weird thing than most people are. So it's an interesting thing to do with kids. This is, again, like number line on the floor in your room. Kids are making jumps. and you're thinking about direction and time. And then they can make their own problems, okay? All right. Integer multiplication, there are some just general ideas here. So for any integers a and b, if a is greater than 0 and b is greater than 0, or they're both less than 0, then a times b is the absolute value of a times b. Okay? So think about it this way. If I had 3 times 4, both of them greater than 0, or negative 3 times negative 4, it's going to end up with 12. So it's the absolute value of the product when the signs are the same. When the signs are different, one of these, a or b, is less than 0 and the other is greater than 0, then the answer of a times b is the absolute value of ab with a negative out front. Okay, so it could be negative 3 times 4. It could be 3 times negative 4. But whichever way you slice it, the answer is going to be negative. Okay? There are some additional properties. It's closed if a and b is a unique integer in the set. Multiplication is commutative. We know this. Multiplication is still associative. We know this. 1 is still the identity. Anything multiplied by 1 is itself. Distributive property still works. Anything times 0 is still 0. Okay, none of the main properties that we've learned with multiplication all along have changed by introducing a negative number. Okay. If a, b, and c are in the set of integers, negative 1 times a is negative a, right? This is the one we started with. Negative a times b is the same as b times negative a, is the same as negative whatever the product of a and b is. Okay? Negative times negative gets me positive. Again, we can distribute multiplication over addition and subtraction, so this is multiplication over subtraction. All right. When we use properties of integer multiplication, we can simplify, right? We can, what do we call it when we do that? When we, what's this action? This is distributing, right? So what we can do is multiply our integers in. So this would be negative 3 times x gets me negative 3x. Negative 3 times negative 2 is a positive 6. When I multiply something like this, what was this called? Do you remember? We use FOIL to do it, right? But this is, if you recognize it, this is actually when the signs are this different like this, but the things being multiplied are exactly the same. This is called the difference of squares, which apparently I'm having a hard time writing this morning. Difference of squares. Okay, this should get you back to your algebra. So first, outer, inner, last, right? Gets me a squared minus ab plus ab minus b squared, which gets me a squared minus b squared. Hence, the difference of squares. Perfect square minus perfect square. All right, same thing here. You would FOIL again, right? So take a minute, work through these. For this one, you should get 16 minus b squared as your final answer. For this one over here, you actually get the same thing, right? 16 minus b squared, because negative 4 times negative 4 is still positive 16. And this guy is tricky. Remember that it is not ever okay to distribute an exponent like that. Oops, I need an eraser. Okay, so we don't do that like that. We FOIL. So this is really x plus 3, that quantity, times x plus 3, right? So this minus x minus 3 times x minus 3. So take a minute, work through. Okay, so the first side, you should get x squared plus 6x plus 9, and then minus the whole thing, right? X squared plus 6x, or sorry, minus 6x plus 9. So then what we need to do to clean this up is distribute our negative, right? It doesn't cancel everything, cancel some. So I'm going to have x squared plus 6x plus 9, that part doesn't change, minus x squared plus 6x minus 9. So now we combine everything together. The x squareds cancel. The 9s cancel. All I get is 6x plus 6x, which is 12x. Okay, so we use the properties of integers to simplify, to distribute. We can also use the properties of integers to factor. It's just the opposite of distributing, right? So here I have AB minus AC. The common term is A, pull it to the front. Here, BA minus CA, common term is A. We would generally pull that to the front, but it can also go back here. Still multiplication. We can write addition or subtraction the same way. This is called factored form. A common term has been factored out. Difference of squares and the distributive properties are used for factoring. Okay, so here are a couple of to try. Factoring should be familiar, but remember, you have to recognize when something's a perfect square, or sorry, a difference of squares. This is something you have seen before and should be able to go like, oh yeah. So when it's a difference of squares, it's always one factor has a plus sign and one has a minus sign. And it's whatever the base of what the square is, x plus 3 and x minus 3. Okay? This guy over here at the end, you look at, we could multiply it through, but actually there's no common terms here. So this can't be factored anyway. There's nothing common there to take out. What's the common term here? Well, it should be x, y, right? They both have that. That leaves me minus 3 plus 5 in parentheses, which you can simplify. Okay, so I got fxy times 2 just gets me 2xy. All right, what's the common term here? The 3, right? So take out a 3. Take a 3 from 3x, leaves x. Take a 3 from 6, leaves 2. Oh, I need to extend my page a little. Here's the last one. What's the common term? It's x squared, right? X squared, 5 minus 2. And that gets me a total of 3 times x squared. Now I'm sure you noticed that you could do these as subtraction. You can do that either way, it's fine. However, it is useful to pay attention to the idea that you could also treat this as a factoring problem. It's nice to be able to see it both ways. All right, for division, once you've done all the multiplication rules and kids understand how multiplication of integers works and when signs are what, division isn't a big deal, okay? And it is not super useful to go to chip models at this point. Most of the time, kids get to hear and they're like, yeah, chips, we get it. And they're kind of over it. So you just sort of move to division and remind them how to treat signs like they did in multiplication. So if a and b are integers, then a divided by b is the unique integer c if it exists such that a equals b times c. When something is divisible, right? And we're not talking about fractions here. So we're not dividing. If something doesn't divide evenly, there is no answer. There's no integer answer, okay? So the quotient of two negative integers is positive if it exists. The quotient of positive and negative is negative, okay? Quotient of two positive integers we knew is positive, right? So if we do 12 divided by negative 4, negative and positive give me negative. Negative 12 divided by 4, negative and positive give me negative. Negative 12 divided by negative 4 should get me a positive, negative and negative. And negative 12 divided by 5 would get me a negative answer, but it's not an integer. It's not divisible. So in this case, we're not going to have an integer answer to this. All right. We continue to come back and forth to order of operations. Here it is again. So now we've got negative numbers, and integers in multiplication and division inside of the mix of what we're doing here. So just be aware, and there will be more practice here. So take a minute, sit down, try these, please. Okay? Think about what you're doing first in each case. All right, so you paused, you worked them through. So for this one, I would do -5 times 4 first, and then I'd rewrite -2 minus 20 plus 1. 2 minus 20 is -18. Plus 1 gets me -17. True? Okay. For the next one, we do parentheses first. So I have a -3 times a 4 plus 1. So now we do multiplication, gets me -12 plus 1 gets me -11. All right, more complicated. Ooh, and there's more at the bottom. So if you haven't done these, take a second. Well, we'll talk about them. All right, the next one, what did you do first? Well, I'm going to do that, and then I'm going to do the other multiplication. 2 minus -3 times, minus 3 times 4 give me -12. Plus 5 times 2 is 10. Minus 1 plus 5. Now addition and subtraction from left to right. Okay, 2 minus 12 is -10. Plus 10 minus 1 plus 5. Minus 10 plus 10 gets me 0, right? Minus 1 plus 5 gets me 4. All right, let's do this next one over here. Division first here, right? So 2 plus what's 16 divided by 4 is 4 times 2 plus 8. Now multiplication. 2 plus 8 plus 8. And now you can add. It's just addition, so it's commutative or associative. You do it whatever order you want. 2 plus 8 is 10, plus another 8 is 18. All right. Remember that this and this mean different things. This is a -3 to the 4th power. This is -3 times -3 times -3 times -3. That is 81. This, and if you put it in your calculator in your phone, you'll see this, really is this. Okay? This 4 applies here. So the answer in this case, oops, is a -81. Okay? All right, one more little bit here. If we have integer numbers, one of the things that can be hard for kids is putting them in order if they're not comfortable with the number line, right? So if I have integers a and b, a is less than b, a is less than b, if and only if, there exists a positive integer k such that a plus k is b. So a is less than b if there's something that I can add to a to get b. B can also be greater than a if and only if b minus a is a positive integer and greater than 0. So if x is less than y and n is an integer, x plus n is less than y plus n. If they were less than each other to start, if x was less than to start, adding the same thing to each number makes it continue to be less than. If x is less than y, doing the opposite of everything means -x is greater than -y. If x is less than y and n is greater than 0, if I multiply everything by n, then it's still the same relationship. Multiple, like this would be like saying -2 is less than 2. If I multiplied both of them by 3, it would still be less, right? If x is less than y and I multiply by something less than 0 by a negative number, it changes the direction of the relationship, okay? This would be like -3 times -2, then becomes greater than 2 times -3, right? Okay. And then let's see what the end here. This is simply just solving, right? So find everything that satisfies the following. I'm going to take away 3 from each side. X is less than -5. Here, I'm going to add 3 to both sides. This is just solving equations, right? -x is less than 8, but what happens when I make this x positive? technically, I'm dividing through by -1. And when I do that, I have to flip the sign. So x is greater than -8. If x is less than -2, what are the values of 5 minus 3x? Oh, I think I took this one off because it's just a convoluted question. All right, so this is the end of 5.2. It was pretty short. If you have questions, please reach out and ask, and you have the rest of the assignments in this module. Thanks.